So this is the 17th podcast of the Physics Chemistry Grade 9 series and the first physics podcast in that series, and it's an introduction to forces. Understanding what forces can and cannot do is one of the most fundamental aspects of physics, as Newton in the picture can tell you. Forces play a very large part in our lives, but we don't often think about the forces that do that. But what can forces do to something? So they can push or pull something, bend or break something, speed up, get something moving, or slow it down, or even stop it, and change its shape. In fact, forces can even heat an object up, or as if by magic cause it to move without anything even touching it. In general, forces, unlike matter, cannot be seen, so are often taken for granted. Now, we all know if you shove somebody, they're going to move. If you bend a ruler too far, it's going to break. But there are some less obvious forces that we need to consider as well. So let's take a look at those. Friction, first of all. Now, Leonardo da Vinci, a great artist and scientist, was one of the first scholars to study friction in any depth. Now, this diagram here shows how friction acts on an object which is sitting on a slope. So here, the blue wedge, we have a slope, and we have a grey box sitting on the slope, and the box isn't moving. Gravity, another force, is trying to pull it down the slope, but friction is working against that, and it's stopping the box from moving. If we give the box some wheels, however, we'll tend to reduce the amount of friction between the box and the surface, and this may happen. Let's watch that again. It will tend to slide down the hill, not jump back up it, but slide down it. Friction can also heat something up. Take a look at this little animation here. A physics book and a chemistry book sitting on each other. If I move one of the books across the other book like this, we can see the particles. We have a thermometer there. The thermometer is rising as it gets hotter, and you can see the particles starting to move more vigorously, which means they've got more energy, and they're all starting to go off because they're getting so hot. If I stop rubbing, then the temperature cools down again. So friction can generate quite a lot of heat. Just rub your hands together if you're not so sure about that. Gravity. When Newton was wandering about in an apple orchard in 1666, apparently a falling apple prompted him to work on his theories of gravity. And this is the first of three non-contact forces. Non-contact because, unlike shoving somebody to get them to move, an apple will fall to the ground without even touching the ground. It's attracted to the ground, but it doesn't have to touch it. This diagram here shows the Earth and the Moon, and this green arrow represents the force on the Moon from the Earth. And as a result of that force, the Moon stays in orbit around the Earth. Now, it's not only big objects that have a gravitational pull, a gravitational force on small objects. This applet shows the gravitational force acting between much smaller masses. So in this picture here, we have a mass of 38 kilograms and a mass of 25 kilograms. These black arrows show the gravitational forces attracting these two objects together. They're very, very small, the forces, a tiny, tiny fraction of a Newton in both cases. If I separate them even further, you can see the arrows shrink down and the force gets even smaller. As I bring them closer together, the force increases. If I increase the mass of these objects, we can see also that those forces increase. Electrostatic force. Charles Augustin de Coulomb in 1784 was the first person to study the force between charged particles such as protons and electrons. Not that he worked with those sort of things, however. He probably worked with balloons or other such objects and asked himself why, when you rub a balloon on your head, does it stick to the wall? So in this applet we have a balloon and a wall, but no head, but we've got a pullover instead, and you can see the charged particles in the pullover are relatively spread out and balanced. If I take the balloon and I rub it on the pullover, the balloon gains a negative charge. The pullover loses some of its negative charge, and as a result they're opposite. And they now attract quite strongly together. I can even get the balloon to stick to the wall, because as I move it close to the wall, it repels negative charges, leaving the surface positively charged. And if it's close enough, not close enough, if it's close enough, it will stick. Like that. The last non-contact force is the magnetic force, which has been known about for a very long time, but more recently it's been linked to the electrostatic force. Of course, you know, if we have two magnets and we put like poles together, like north and north or south and south, they will push apart, they will repel. And these green arrows here show the force pushing these two things apart. If we put two like opposite poles next to each other, north and south, for example, they will attract, and we can see the green arrows are reversed, showing that the force is pulling those two together. Often in physics we need to measure forces, and of course we can measure them using various instruments, and we have a standard unit of force, and that's called the Newton. Newton gave his name to the standard unit of force. Now 1 Newton of force is defined as the force needed to accelerate a mass of 1 kilogram at a constant rate of 1 meter per second squared. And let's have a look at this picture to see if we can understand what that means. So here's a kilogram of mass. There is a force of 1 Newton pushing it, and as a result of that force, the object speeds up. It speeds up at a rate of 1 meter per second every second, or 1 meter per second squared. To actually measure those newtons of force, we have various pieces of equipment, as I've said. Let's take a look at 3 of them here. Firstly, we have a scale. This one looks very much like, and probably is, a bathroom scale. If you stand on this, you are measuring a force. You are measuring the force of gravity on yourself. We often just call that weight. Here we have a force sensor. We use technology a lot more these days, and this electronic sensor is hooked up to data logging equipment and can measure push or pull forces. The final one I've got here is a simple spring balance. Again, you can hang things on that, you can measure their weight, the force of gravity on them, or you can pull things, but they're not really used for push forces. So in summary, forces generally cannot be seen, but they're very, very important to our lives, and they really control our lives. We can measure forces very easily using some of the pieces of equipment we've just looked at. And there are several very important forces that really do control our lives, such as gravity and friction, and these are the 2 forces in particular that we're going to be taking a closer look at in the next couple of podcasts.